anytime a company comes in and saves me time and saves the effort that I've had to spend in the design and in the calculations, whether it's load inertia calculations or whatever it is, anytime somebody comes in and helps me in that effort, I'm certainly very grateful.
Every time Compumotors come out with something new, I've seen it as a step ahead.
And in the case of Compumotor, they'd done their homework, and they were offering some of the most advanced technologies for the most affordable prices.
The question is, what does throughput translate into? And the bottom line is money.
Compumotor is in the business of providing reliable solutions to motion control applications. Prior to 1979, many design engineers would not consider using open-loop motion control technology. Compumotor changed that attitude with the release of the world's first microstepping drive. Today, we are the world's #1 manufacturer of microstepping products. We are also recognized as the industry's technological leader. Our product innovations have opened the door to thousands of new applications. We continue to invest heavily in research and development. And today, once again, we raise the bar for motion control performance and reliability with our latest microstepping product, the Zeta drive.
The Zeta series provides a user-friendly system that delivers high performance and reliability in 2 packages, the Zeta 4 drive and the Zeta 6104 drive indexer. The entire series incorporates the breakthrough techniques known as active damping and electronic viscosity. The Zeta drive is perfect for any multi-axis application and allows control by any standard step and direction or clockwise counterclockwise indexer. The Zeta 6104 builds upon the power and reliability of Compumotor's 6000 series of indexers by combining drive and indexer in one package. This fusion of innovative features makes the Zeta series the smallest, highest performing, and most cost-effective microstepping system available today.
We have a product recognition award for Parker Hannifin Compumotor Division, Zeta Series Microstepping System.
With the Compumotor stepper motor systems that we've used in each and every instance have been a legitimate progression forward. The Zeta, in some senses, is a bigger step than others because it's taking into account a more adaptive approach to the motor control right at the drive level, which I haven't seen before, had thought about, but apparently people at Compumotor were doing the same.
But I see the relationship of the stepper motor and the gearbox becoming much more useful based on the Zeta drive. Customers over the years have learned not to put stepper motors and gearboxes together as a general package simply because of the resonance problems they've had. And I see the Zeta removing that restraint, which means that customers can use smaller motors, lighter packages, get more performance within the same package size.
In incorporating the Zeta drive, we're seeing a dramatic improvement in the throughput performance on a 24-inch lead screw, a reduction in noise, and an overall smoothness that I know our customers will appreciate.
We had an application on an existing design where we were producing an outside diameter on our drills, and we were moving approximately 4.5 inches distance from the cutting workpiece to the from the cutting wheel to the center of the workpiece where a robot would load and unload the tool. So the distance there was about 4.5 inches. And it was a good machine and reliable, but we had difficulty because we were spending a little more time, cycle time, producing those tools that we really wanted. And so we decided to investigate a possibility of making that 4.5-inch move a little faster than we are currently making it. And with the initial design, that was about 4.5 seconds. We would spend 4.5 seconds making that 4.5-inch move. And we were trying to find a faster way of making that move, because that would directly translate in reduction of the cycle time. And so we've decided to bring in 3 companies, one of which was Compumotor, of course, and the Zeta drive. And we were very clear at the initial startup with all 3 people that whoever makes that move faster will really get the contract for the drives, because it was that critical.
When the rotor of a step motor loses synchronization with the stator's magnetic field, the motor will tend to lose torque and stall. This can happen when the motor is instructed to perform a move that requires more torque than is available. It can also happen when the motor vibrates due to resonances so violently that the available torque is not adequate to overcome the oscillations and maintain control over the motor. These characteristic vibrations or oscillations have limited the popularity of step motor technology, particularly when the ringing occurs at the end of the move. This oscillatory behavior can significantly impact the performance of an operation even if the motor doesn't stall. The ringing that happens at the end of a motion profile can extend cycle times as much as a second or more, delaying operations that require the motor to completely settle, thereby extending cycle times and limiting system throughput.
That disc is attached to the back of the motor shaft to illustrate the vibrations and oscillations that can occur in an undamped system. As you can see, the system is unstable. There's a lot of ringing occurring at the end of each move.
This oscillatory behavior is characteristic of all motors and is very predictable. The motor system can be modeled as a mass at the end of a spring. As the spring is repositioned, the mass will attempt to follow, then oscillate around its equilibrium at a rate and duration dictated by the characteristics of the spring and load. The potential for oscillation is why 50% torque margins are applied to step motor systems. The objective is to have some amount of torque set aside to combat these tendencies to oscillate and keep the motor under control. An alternative solution is to damp the system. Traditionally, this is done by adding feedback devices and electronics, as is the case with servo systems, or by adding mechanical dampers. However, these approaches can significantly impact the overall cost and dynamics of the system. Some mechanical dampers can cost as much as 2 to 3 times the cost of the motor. The Zeta represents the next major evolution in motion technology, eliminating many of the undesirable performance characteristics typical of step motor systems through Compumotor's patented damping technologies. The Zeta's electronic viscosity and active damping features allow the user to realize a motor's full potential. They provide so much additional control over oscillatory behavior that 50% torque margins have become a thing of the past. This means with your motor, the Zeta gives you significantly more usable torque. With this motor, the Zeta outperforms the competition in this way. All you do is engage these technologies and the motor becomes smoother, more stable and responsive, having a major impact on your system throughput.
As you can see, the system is unstable. Ringing is occurring at the end of each move. As I increase the Zeta's damping, the system becomes stable and the ringing is eliminated.
In addition to the damping features of the Zeta, our customers see a significant advantage in the more basic features of the product. By expanding on the success of its predecessor, the Zeta's smaller package size, reduced cost, and overall product reliability make it an obvious choice for many applications.
The Zeta drive is an easy recommendation, particularly to people who've had Compumotor before. Compactness of design, price are big plus, and a couple of the age-old bugaboos addressed, I think, in a very firm fashion. The low-range native resonance problem as well as the mid-band instability and resonance difficulty that we've all looked at for all these years. To do that at that price and that size, that's a great way to go.
Even a microstepping drive has a primary resonance point. If you carefully look for it, you will find there's a point, usually a slow speed, where the motor will start to oscillate and rattle. The Zeta drive significantly reduces that over the other microstepping drives that we've been working with.
As an OEM developer of video image system products that incorporate motion control, and myself as a design engineer, I was particularly interested in the quality and aspects of the Zeta drive that complemented our own product quality and quality assurance. The test and evaluation was simple. We were able to apply the Zeta drive control immediately to our product by removing our own in-house drive and test and validate its performance enhancements with a dramatic result.
We were very clear at the initial startup with all three people that whoever makes it move faster will really get the contract for the drives, because it was that critical. We actually ran production. We kept on slowly speeding it up with each machine until the machine would actually stall out and could no longer go any faster or accelerate any faster. And the Zeta drive was the most successful because it was able to beat everybody else. And so we were able to make that move in 1.5 seconds. So that translates up to 6 seconds of total cycle time saving. So we went down from 32 seconds to 26 seconds. That 6 seconds is a huge amount when you're making that many tools.
We have made some big claims about the Zeta series with its patented technology. That's because we stand behind our product and are willing to provide the information you need to make an informed decision. We invite you to contact our application engineering department at 1-800-358-9070 and discuss your application with one of our engineers. Also, you can request the Zeta information from technology articles and brochures, choose Zeta software, and our master catalog. If you would like a personal Zeta throughput demonstration at your facility, we'd be delighted to oblige. Please contact your local Compumotor distributor.
Parker Hannafin, a world-class manufacturer of motion control solutions. Compumotor, setting the standards for service and quality among suppliers of electromechanical positioning systems. Innovator of stepper and servo technologies, introduces the next breakthrough in motion control technology, a revolution in step motor performance, the Zeta drive. The purpose of this video is to introduce Compumotor's next generation micro-stepping drive. Stuart Goodnick, who possesses both a bachelor's degree and master's degree in physics and advanced dynamics, is Compumotor's engineering manager for R&D of power products. He'll demonstrate the groundbreaking benefits of the Zeta drive, then share his expert knowledge on step motor behavior and compensation techniques.
What we have here is Compumotor's next generation microstepping technology, the Zeta drive. In this demonstration, we have the Zeta drive hooked up to a 8393 step motor. Attached to the step motor is a load, which represents a multiple of the rotor inertia. And this system is hooked together and being driven by an indexer, which is in the box. Coupled to the system through an encoder is a position capture 6000 controller board, which we're using for the purposes of this demonstration. What we'd like to demonstrate with this apparatus is Compumotor's new exciting electronic damping technology, which is being introduced in the Zeta microstepping product. What we're going to do is run the motor through a sequence of alternate low and high speed moves and show you the transient response on this oscillograph. So first we'll command the move without any of the electronic damping engaged. We move from low speed to high speed and repeat that cycle. What we'll see on the graph here is the response as measured by the encoder. You can see as we move from low speed to high speed, the rotor, which is coupled directly to the encoder, oscillates about the commanded equilibrium position. In this graph, the vertical axis is velocity, and the horizontal axis is time. You can see that the transitory behavior is taking place on a time frame of approximately 250 milliseconds per cycle of the move. That's a quarter of a second. The step motor actually has not settled in position before we begin the downward acceleration. When we move up with a fast acceleration to our commanded velocity and try to slew at that velocity, the rotor is actually oscillating violently about that equilibrium position, and it never quite settles down until we try to decelerate back down to the lower speed. Once we hit that lower speed, we also oscillate about that equilibrium position, and the move repeats on and on. We will do the same move with the electronic damping engaged. The electronic damping uses electronic means in the drive without any external sensor to electronically control this oscillatory behavior. You'll notice after the position capture that the oscillograph will change dramatically. Notice here now that as we move up to position, although we have a mild transient response, in fact, it gets damped out very quickly, and the motor reaches its commanded velocity and stays there with extreme velocity smoothness. Now, when we do a deceleration, and decelerate down to the very low speed of approximately 0.2 RPS, notice that after an initial transient response, we quickly damp out and settle into our commanded velocity. This represents a dramatic difference between the previous move, which, as you recall, looks like this. With the electronic damping engaged, we're able to virtually eliminate all of that transient oscillation. What this means in terms of your performance on the step motor is that your settling time has been reduced by almost a factor of 10. We're now settling in approximately 25 milliseconds, whereas before it required 250 milliseconds, and we still hadn't settled out into our commanded velocity. In addition, when we try to make these hard downward accelerations, a great deal of the torque of the step motor itself is consumed in fighting these transient oscillations. When we derate a step motor and recommend that you use a 50% torque margin when applying a step motor in an application, that torque margin is there to ensure that you don't lose synchronization because of fighting transients introduced by your move profile. Now, with the damping technology engaged, torque margins are a thing of the past. You see now that we have such tight control over the rotor position and the rotor velocity that when we begin our downward deceleration, almost all of the torque is available now for the dynamics of the move, and we're not wasting torque fighting transient oscillation. What this means in terms of your move itself can be seen by a series of very fast, high-velocity moves. With the damping technology turned off, when I try to make this fast, repeated move, you'll notice that the rotor will lose synchronization at certain points because my torque utilization is exceeding the torque margin I need because of the transient activity. You can hear that scratchiness. That represents the slipping of the step motor. Now, if we turn the damping technology on, you can hear we don't have that same stalling effect. What we've done here with the damping technology in Compumotor's new Zeta drive is provide a technology which significantly reduces the settling time of the step motor. We go down by a factor of 10, which means greater machine throughput in any sort of machine cycle on which this motor is applied. In addition to that, by controlling the transient activity at velocity, we're able to significantly improve the efficiency of torque utilization in the motor. This means in a practical application that you may be able to do the same job with a smaller motor and hence save significant system cost. Traditionally, these problems were solved with mechanical and electronic techniques that added cost and complexity to the system.
Reduced settling time, greater throughput, better torque utilization. The Zeta drive brings these benefits, typically associated with servo systems, to step motor technology, eliminating many of the concerns traditionally associated with open-loop systems. The Zeta drive translates into greater productivity for existing mechanical systems. More parts per minute, more cycles per hour, less time and material waste. As with servo systems, the Zeta drive combats oscillatory behavior. Its full-range damping control goes far beyond traditional anti-resonant circuits and mechanical dampers. The Zeta drive combines these performance benefits with the user-friendly packaging you've come to expect from Compumotor.
What we've achieved with Compumotor's new Zeta microstepping drive is the control of oscillatory behavior and the improvement of efficient torque utilization in the step motor system without additional cost to the customer. What we've achieved is a new benchmark in microstepping technology. We've basically ushered in the next platform generation of microstepping drive technology, the Zeta drive. The title of this presentation is Damping of Microstepping Systems, a Performance Review. And we have three objectives in this presentation. The first objective is to introduce you to the background of step motor systems and the technology. What is a step motor and how does it operate? The second objective is to describe the transient behavior of a step motor and some of the issues associated with this technology that get in the way of good solid positioning. And the third objective is to describe the technology that's used to address these problems. And all of these are by way of introducing a new electronic technology that we're incorporating into our next generation step motor drive, the Zeta drive. To begin with, the step motor has two primary components. The first is the rotor, and the second is the stator. And the way that the rotor and the stator interact together gives us understanding of how the step motor actually creates motion. The rotor consists of a stack of what are called laminations. A lamination is a thin piece of metal. In this case, this blow-up of a rotor lamination consists of a series of teeth around a circumference. What we do is put stacks of these laminations together to form what we call the lamination stack, and between alternate stacks of the laminations, we put a permanent magnet. The rotor assembly consists of an alternate set of lamination stacks, and they look something like this, that basically we have what are called pole pieces, and each of the pole pieces has a series of matching teeth to the teeth on the rotor lamination stack. We stack the lamination pieces together to form a long tube, and about those pole pieces we wrap wire to create a series of coupled electromagnets. We have 8 different pole pieces, and we couple the electromagnets in pairs so that we have 4 distinct phases. With a typical 4-phase step motor like this, if I then couple the alternate pairs of phases together, I'm able to create what we call the 2-phase permanent magnet hybrid stepping motor. The way that the teeth interact give us understanding about how a step motor holds position, and also how we're able to move the step motor from position to position. If I energize the windings of one of the phases or one of the pole pieces of the step motor, that creates a magnetic field. That magnetic field interacts with the permanent magnetic field being produced by the magnet in the rotor, and the tendency is for the teeth of the rotor to line up with the teeth of the stator, that is the energized electromagnet. And you can see in this diagram a picture where we have perfect alignment. What we do with this step motor stator assembly is to actually spatially phase the sets of teeth in alternate pole pieces in such a way that when one set of teeth, or one pair of teeth are on the stator are aligned with the teeth on the rotor, that the next piece over here, the next pole piece here, has teeth that are actually 1/4 tooth interval misaligned. And you can see that in this diagram here. The next pair, which is coupled with the phase A, are then a full half-tooth interval misaligned, and so on. So basically, when I have one phase energized and the teeth are perfectly aligned in that phase or in that stator piece, the teeth are misaligned in all the other pole pieces. I can use this technique in order to create motion. What I do is energize the phase A of the step motor, and I cause the teeth of the rotor to align up to the teeth in the stator. Now, if I de-energize phase A, drop its current to 0, and then energize phase B, what happens is that those teeth that were 1/4 tooth misaligned from the rotor to the stator of phase B now are going to pull into alignment. That pulling into alignment causes the rotor to move. This is how we actually create motion in the step motor. I cycle or I step through alternate configurations of electromagnetic fields in phase A and phase B, and that causes the rotor to respond or move or to be dragged by the magnetic field. I'm not actually turning the step motor directly. And many times when people think about a step motor, they think of a ratchet and trowel, but there's no mechanical connection. I'm dragging the rotor around by moving electromagnetic fields in the phase A and phase B stator assemblies. This diagram here shows the technique called full stepping of a step motor. The basic idea goes as follows. I energize phase A and cause the teeth of the rotor to align with the teeth of phase A stator. I then de-energize phase A and energize phase B, as we said, and that causes the rotor to realign itself with the phase B stator teeth. That is, it moves a quarter tooth interval. And then I de-energize phase B and energize phase A in the opposite direction, and because of the phasing of the teeth on each of these pole pieces, I then move another quarter tooth interval. This full stepping technique defines 4 distinct positions for each tooth interval. I have 50 teeth around the circumference of this step motor, and so that defines 200 distinct positions. I've defined a 200 step per revolution step motor, and that's what full stepping means. To get into the dynamic model of the step motor, we need to study the tooth-to-tooth interaction between the rotor teeth and the stator teeth. When you look at the force that's created when the teeth in the rotor and the teeth of the stator are aligned, you can see that we create a series of stable and unstable points. When the teeth are aligned, the rotor holds still. If you try to twist the shaft on the rotor, you'll find that there's a torque that's trying to fight that action. That can be shown schematically in the diagram on the slide here. You can see that we have a series of stable points, and the stable points have a certain amount of peak torque associated with them. In other words, if I turn the rotor with enough torque, I can actually cause myself to slip from one tooth to the next tooth. For a 50-pole step motor, we actually have a 50-way symmetry, where I can actually, one pole position is indistinguishable from the other pole position. If I look at the mathematical modeling of this structure that we've created here, I see that it actually models very much like a mass on a spring. In this case, when I'm sitting at the stable point, the rotor is in equilibrium with the stator. The mass in my mass spring model here is the inertia of the rotor plus the inertia of the load that I'm coupled to. The spring in this case is the spring that's created by the magnetic interaction between the permanent magnet field in the rotor and the electromagnetic field that I'm creating by energizing the stator assembly. So there's a certain stiffness associated with that, and you can see that the stiffness is given in the sine wave diagram here. If you have a step motor that has a peak torque of some value, the stiffness in terms of our mass spring model actually turns out to be 50, the number of teeth, times the peak torque. Now, the reason why this is important to understand this model is that, like a mass spring system, a step motor rotor actually oscillates about its equilibrium position. In the same way that if I move a mass on the end of a slinky, and you see that that mass takes a while before it settles into a stable position, when I move a step motor rotor from one step to the next step, I actually see the rotor oscillating about the equilibrium position until it finally settles down into a stable position. Now, most of the applications in which step motors are applied are called point-to-point positioning applications, and it's important that we settle out as quickly as possible. Undue oscillations limit the amount of dynamic performance I can get out of this system. In order to go into a little more mathematical detail in this model, we have here the transfer function for the step motor and load system. The omega in this transfer function represents the resonant frequency, which depends on the stiffness or the magnetic field in my system and the total inertia. The zeta represents the damping ratio, which we'll describe in a moment. To understand this mathematical abstraction, it's best to look at what's called a Bode plot here. In the Bode plot, we see a comparison between input frequency or position command and response of the rotor assembly. You can see in this diagram that there's a resonant peak, or a point of exaggerated response when I try to move the step motor at a certain velocity. That resonance is the only resonance that exists in the system. It's a resonance that is actually given by the square root of the stiffness divided by the inertia of the system. The point to remember here is that there's one resonance in the system. Anytime a step motor is oscillating, it's oscillating at a given frequency, and that frequency depends on the amount of load that I put on the step motor application system. What that means practically is that anytime I make a step from one position to the next position, as you can see in this diagram, whether that's a microstep, whether it's a full step, whether I'm using a 5-phase step motor system or whether I'm using a more standard 2-phase system, the rotor is going to oscillate about the equilibrium position. The amount of time it takes to settle down into position is a critical application parameter that depends on how well I can use the step motor in a positioning application. As you can see in this diagram, the damping ratio basically is a mathematical index that tells us how fast the system actually settles down into position. So when I move the rotor from one position to the next position, the damping ratio tells me how fast that transient oscillation dies down and the rotor is finally in a usable, stable position. For a step motor system is a relatively undamped system. The only damping comes about because of the viscosity of the bearing grease and some minor eddy current interactions due to the magnetic structure of the motor. There's very little else that damps the step motor. So typically, an undamped step motor system has a zeta of approximately 0.04. What that means practically is, for a typical resonant frequency of 100 hertz, that the step motor actually can take over 250 milliseconds to settle into position. That's a quarter of a second for the step motor to actually settle into a stable position. You can easily imagine then that if I'm trying to do point-to-point positioning and I depend on being in a stable position before I engage in the next machine cycle, that this can seriously limit the usability of the step motor in a motion control application. So when are transients a problem with a step motor system? Well, there are a number of applications where these transient issues we've described really get in the way of the effectiveness in which we can apply a step motor. There are many applications where a step motor is used just to move something from one position to the next, and we don't really care about this transient oscillation. But there's a number of applications where it is important. Applications where settling time is an issue are probably the biggest area where the transient oscillation of a step motor has to be addressed. Such applications require that we get into position very quickly before we can start the next machine cycle, and so throughput becomes an issue there. What we want to do then is to find some means to control that transient activity. Another class of applications that are where this transient activity is important are high acceleration rates. Basically, an application where you want to move from one position to the next position very quickly, you don't necessarily care about settling out, but you really want to move the step motor as fast as possible, can be affected by this transient oscillation. What happens is, when you move to velocity, when you actually accelerate the step motor up to its full speed, we excite that resonant activity we described previously. When I try to accelerate up to constant speed, I'll be oscillating about my equilibrium position, even though that equilibrium position is now moving at a constant velocity. The problem comes when I want to decelerate. If the rotor is still oscillating somewhat when I'm trying to decelerate, then the amount of torque that I'm able to use in the step motor for that deceleration gets compromised by having to use some of that torque to overcome the transient activity of the rotor. Basically, the ratings for a step motor contain a peak torque figure. In practical applications, I can't use that full peak torque to make a fast deceleration because I have to reserve some of the inherent torque in that step motor in order to control or overcome the transient activity I might be experiencing when I want to decelerate from constant velocity to rest. Another class of application where this transient behavior of the step motor can be a problem are in cases where mid-frequency resonance appears. Mid-frequency resonance is a parasitic effect that occurs with the interaction of the back EMF generated by the step motor and the current control loops we use in the drive to maintain full current in the windings of the motor. Usually mid-frequency resonance occurs around the speeds of 15 RPS, or revolutions per second. And what happens is a destabilizing a positive feedback, which when the motor is undamped causes the step motor to stall or lose synchronization. Even a modest amount of damping in a system can control mid-frequency resonance, but there are some applications where we don't have that luxury, and so mid-frequency resonance can limit the speed range in which I can operate the step motor. A couple of practical examples of these types of applications where we have to control transients are pick-and-place machines. For instance, when you're trying to pick electronic components from one location and place them on a PC board in an automated assembly machine. That's an application where settling time is critically related to the throughput of the machine, or the speed at which we can pick parts up and place them down on a PC board. Applications where mid-frequency resonance comes into play are linear actuator applications, where the step motor is attached to a lead screw, and that lead screw is actually extending out a linear arm for some sort of positioning application on a larger machine. Often in cases like that, we can have problems with mid-frequency resonance, and what that means is we lose a certain amount of our forward force from the linear actuator at certain speeds, certain rotation speeds of the step motor. So when we refer to damping, what we mean is we're trying to damp out the amplitude of oscillations in the mechanical system. Basically, damping is the progressive diminishing of the amplitude of the oscillation. When we refer to an object like a damper is a means, whether it's a mechanical means or an electronic means, for controlling this kind of reduction of amplitude of the mechanical system. An undamped oscillation will continue forever, and as we say, we use step motors for point-to-point positioning applications. So the object of the design goal of the system is to put damping into the mechanics or into the electronics in some way so that we can control and improve our positioning ability. So our problem here is that we want to damp out all the transients in the step motor system. Well, there are two primary strategies which we employ for doing this. The first strategy, we try to minimize transient excitation. In the second strategy, we're actually modifying the system dynamics as a means to control oscillations in the mechanical system. When we minimize transient excitations, there are two primary techniques that have been employed. One is called microstepping, and one is called profile compensation. Microstepping is perhaps the most popular and effective means for controlling undue oscillations in a step motor system. Microstepping was originally introduced into industrial systems by Compumotor in 1979. And the strategy with microstepping is to reduce the actual step size when we move from position to position with the step motor system. The idea here is that by making the step size smaller, we actually limit the amplitude of that transient activity which we excite. If you recall in the previous diagram, when we make a step move with a step motor, we see that the rotor actually responds by oscillating about the equilibrium position. Well, the amplitude of that oscillation depends on the size of the step. So with microstepping, my strategy is to make a smaller step size and thereby reduce the amount of oscillation of that one resonance in the step motor. Microstepping doesn't really reduce or change the frequency of the oscillation. I'm not changing the system here. I'm just trying to work around the native dynamics of the step motor. To see what this represents in terms of current and the windings of each of the phases, you can see this diagram on the slide is a schematic way of representing the energized currents in each of the phases of the step motor. Each point represents a position. The axes represent phase A and phase B. If you look at the point on the phase A axis, that represents a point where phase A is fully energized and phase B has no current. In the full stepping techniques we described earlier in this presentation, my means of positioning or moving the step motor from point to point represents going from the position on the A axis, where I'm fully energized in phase A and have zero current in phase B, to the next point on the phase B axis, where phase B has full value and phase A has zero value. That's full stepping. And what that represents in terms of the teeth of the step motor is defining 4 distinct positions between each of these teeth. So for a 50-pole step motor, my full stepping strategy allows me 200 distinct steps for the full revolution of the step motor. With microstepping, what I do in my microstepping drive is develop a means to actually control the currents and the windings of the motor a little more precisely than I do with full stepping. So what I actually do here is I can have phase A almost fully energized and phase B just a little bit energized to define a point that's off axis there. That represents the little point you see above the point on our full stepping point on the phase A axis. So by defining each small gradations in current with phase A and phase B, what I'm actually doing is moving the equilibrium point to which this rotor will sit with respect to the stator teeth, point by point or gradually. So I can actually position between points where the teeth would normally be aligned. That's the strategy of microstepping. Profile compensation represents a control technique where we're actually applying acceleration feed forward to the position command. The way of thinking about this is that what I'm doing with this feed forward is preloading my torque angle curve. And the best analogy to use to visualize this is to think about a mass on the end of a spring. What we're doing with our profile compensation is actually stretching the spring before we try to move the mass. You can imagine here, suppose that I have a mass sitting on the table and I have a spring attached to that mass. Okay? The way that we traditionally cause a step motor to move is by trying to move the end of the spring. You see, when we cycle the currents in the phases of the motor, we're moving that electromagnet stable point around. We're actually controlling the end of the spring. We're not touching the rotor directly. We're only influencing the rotor indirectly through the coupling of the magnetic field to the rotor, the field, and the rotor. Or in terms of our spring, I'm only affecting the mass on the table in terms of the spring here. So if I try to accelerate this mass off of the table, the way I would do this in my traditional stepping technology is by accelerating the end of the spring here. Well, what would happen practically is that the spring would stretch, and eventually there'd be enough force that the mass would lift off the table. Well, when that happens, you can all see intuitively that the mass is going to oscillate about its equilibrium position as I continue my acceleration. Well, what I do with profile compensation is actually preload the spring. I know that since I have a mass with a certain value, and I know that I have a spring with a certain spring constant, instead of just lifting the end of the spring off the table, if I instantaneously stretch that string to the extension that it's going to maintain under constant acceleration, and then start accelerating, what happens is the mass just lifts very easily off the table and there's no transient activity that's been excited. So with profile compensation, what we're doing is eliminating the transients caused by abrupt acceleration. It doesn't matter if I'm microstepping. It doesn't matter if I'm full stepping or half stepping. When I have that abrupt acceleration, that big impact to my system causes the rotor to oscillate about its equilibrium position. So with profile compensation, if I preload that torque angle curve, I can actually null out the transient response. The only problem is that it doesn't affect random torque disturbances. It only will null out the transients associated with our move profile. So the other means that we use for controlling transient activity in a step motor is to actually modify the system dynamics. There's two primary means that we use to doing this. One is mechanical and one is electronic. And under mechanical, the means that we'll describe are friction rings and ferrofluidic dampers. Under the electronic, there are two means that are traditional: electronic viscosity and actual active damping. So under the category of mechanical damping, probably the lowest tech and oldest means for controlling transient activity in a motion control system are what are called friction rings. We have an example of one type of friction ring here. But friction rings basically provide some way of having a mechanical friction between the load and the motor. Just like it sounds, if I have a mechanical contact, then I'm going to reduce settling time of the step motor. I'm going to introduce some sort of viscous term into my dynamic system. The problem is that to the extent that the friction rings are applied, I'm adding a viscous torque. That torque increases with velocity. So I'm cutting out available torque in a step motor system if I employ friction rings. Well, that can severely limit my dynamic performance because I'm having to use some of the available torque in the motor to provide this damping probably over and above the top of what I need. And besides the limited dynamic performance, because I have a mechanical-to-mechanical contact in friction rings can be subject to wear and may eventually have to be replaced. Probably the most popular and effective means of mechanical damping is the ferrofluidic damper. A ferrofluidic damper, this is an example of one type, is an object which consists of a rigid shell that contains within it a seismic mass. The seismic mass is coupled to the shell via a ferrofluidic material. Now, the mass itself is magnetic, and a ferrofluidic material is a viscous liquid that has suspended within it some sort of magnetic material like iron filings. Now, the rigid shell is rigidly coupled to the shaft of my step motor. When I accelerate this system up to speed, eventually, during the acceleration, there'll be some transient behavior, but the long-term constant velocity behavior of this ferrofluidic damper is for the rigid shell, obviously, to have the same velocity as the rotor of the step motor. If I subject the rotor of the motor to some disturbance, and that sort of disturbance could be a transient excitation, it could be the oscillations about an equilibrium position, or it could be some sort of external force. But any time I disturb that rotor now, the interaction between that seismic mass and the rigid shell introduces a damping term into my mechanical system. The mathematics can be a little bit hairy, but you can actually come out and compute actual zetas that are introduced into the system as a result of including the ferrofluidic damper. Now, this is an effective means. It's easy to apply. The main problem, however, is that in order to get damping ratios of any significant amount, I have to have a fairly large ferrofluidic damper. That means that I'm adding inertia to my system. When I'm adding inertia to my system, I'm limiting my dynamic performance. I'm limiting how fast I can accelerate because I only have so much torque in the step motor. I'm not adding torque, but in order to accelerate at the same rate with more inertia, I have to use more torque. So putting on a big ferrofluidic damper limits my dynamic performance. I think the biggest limitation with the ferrofluidics is that they're very expensive. Sometimes a ferrofluidic damper is more expensive than the step motor you're actually trying to control. So besides mechanical damping, the other means for actually controlling or changing the dynamics of our mechanical system is through electronic damping. There are two main means that we'll discuss here. One is called electronic viscosity, and the other is called active electronic damping. In electronic viscosity, what we're trying to do is to actually modify the drive and motor characteristics. And typically, this is a technique that's been used at the end of a move. Electronic viscosity in the form that we're describing here was originally developed in the early 80s when step motors were being used in printer applications. So a lot of attention was placed on electronic means for damping the step motor because you wanted to stop the print head quickly so that you could do your stroke and make your imprint. Some examples of electronic viscosity that'll give kind of a better sense to what we mean include shorting the motor windings in an unenergized phase of the motor at rest. Now, if we take a step motor, we take the A plus and A minus and short those together, and then we try to turn the shaft of the step motor, we'll notice that there's a force of some sort that's fighting our attempt to turn the shaft. That viscous-like force is due to the fact that when we turn the shaft of the motor is acting like a generator. We're producing a voltage which causes a current to flow through that short circuit we've created. And that current flowing through the resistance and the inductance of the windings of the phase that we've shorted together here requires energy to continue the flow. So we have to provide the energy. That's the force that we're fighting. That causes damping. That's a very strong damping effect and a very effective means for causing fast settling. A similar technique is to take the back EMF that's produced by the phase that is off and feed it into the opposing phase. When a step motor is, again, at rest and one of the phases is known to be have zero current in it, if I measure any current flow in that phase at all through my current sense resistor, I'm going to know that that's because that's current that's reflected of the fact that the rotor is moving back and forth around its equilibrium position and causing a back EMF to appear, which will cause current to flow. Well, if I feed that signal into the current command for the opposing phase, the nature of the complementary phasing of phase A and phase B are such that I actually introduce a damping torque that will fight that transitory motion. So again, that's a very effective means. But both of those means depend on the fact that when I'm at rest, one of the phases of my step motor has zero current in it. These methods don't work very well for microstepping because with microstepping, we may come to rest in a configuration where both phase A and phase B have some current. So I can't use this kind of electronic damping here. Another form of electronic damping is called active damping. And with active damping, it begins with developing an electronic means for actually injecting positive or negative torque into the rotor. The way we do this in a step motor is by developing a circuit which allows us to adjust the phase of the driving waveforms. As you recall from our diagram, which showed the stable and unstable equilibrium points that the rotor sits at when I energize the phases of the motor, if I start moving the location of that active detent curve that I described back and forth, I can actually subject the rotor to small amounts of positive or negative torque. So this is my means for actually injecting torque into the step motor. If I, in turn, use a feedback signal, perhaps from a tachometer on the back of a step motor, to tell me if my step motor is moving where I want it to, then I can use this means of modulating the waveforms to close a damping loop. Basically, if I measure the velocity of the step motor, of the rotor itself, compare that to my commanded velocity, and then close a loop that tries to damp out errors in that velocity, then I can get some very tight, high dynamic damping in my step motor system. The main limitation of these techniques are that the sensors I need and the additional electronics I need to close these loops can be somewhat expensive. And also, when I start putting sensors on the back of a step motor, I start moving away from that key element that makes a step motor so popular. It's easy to use, and there aren't a lot of wires coming back from the step motor. So what Compumotor's done in the last year of active R&D in our step motor system is developed two means for actually improving upon the state-of-the-art with electronic viscosity and with active damping. Compumotor's electronic viscosity is a means for actually modifying the current compensation loop values that we use to control the currents in the phases of the motor. We control those currents through a servo-like loop, and we want to maintain full current in each of the phases of the motor. Well, if we play around with the dynamics of the compensation values, the gains of that little servo loop, if you will, I can create some damping effects at low speeds. The technique that we use engages at lower speeds, say under 3 RPS, and the effect is that I'm able to create electronic damping at rest or at low speed. This goes well beyond the state-of-the-art of electronic viscosity in that not only does it work when the phase currents are non-zero, but it also works at lower speed. What I'm able to do with this technique is significantly reduce the settling time when the step motor actually is running, either settles at rest or actually settles down to a lower velocity. Compumotor's active damping technology uses a similar technique to the active damping technology I described before, except instead of using an external sensor, we've developed an internal sensor, or an observer, which uses the motor terminal voltages and the currents that are flowing in the motor to actually determine information about the velocity of the rotor. This observer actually measures the load acceleration, and we use this acceleration value, scaled appropriately, to develop a damping loop. So the benefits of these techniques are that we now have, with the active damping, a means that is very effective at higher speeds, with the electronic viscosity, a means that is effective at lower speeds, and I'm able to obtain damping ratios on the order of 0.25 to 0.4. Now that's over and above the native damping ratio of a step motor of 0.02. You can see on this diagram that as I go from a damping ratio of 0.01 to 0.2 to 0.35, that the performance and the rate at which the step motor settles out increases significantly. Another benefit of this kind of damping technology is that when I'm moving at speed, I'm less subject to torque disturbances, and so my velocity smoothness increases. So what we've done with our next generation platform of microstepping is introduce the Zeta drive. The Zeta drive incorporates electronic damping, both active damping and electronic viscosity, And we maintain the same high reliability and performance that you've come to expect from Compumotor step motor products. This literally is, both for Compumotor and for the industry, the next generation in microstepping technology.